Hi class, welcome again to another session on digital principles and system design. Today we are going to study about field programmable gate array or FPGA as it is called. So FPGA or field programmable gate arrays have actually revolutionized how electronics is produced and how electronics is used basically. So these are VLSI circuits that can be programmed at the user's location. You know, you're probably too young at the moment, but when you grow up and have an idea of your own and you want to implement that as a hardware, you you wouldn't want to trust a company to do that for you, right? Because of data protection issues, and because the company might, I mean, I'm not saying every company does this, but there are companies which might claim that it is their idea and file for a patent. Just use your brain and use your time, and get the credit for it. So for your own good, you want to have a certain amount of privacy while you are developing a product. And if that product does well, you would want to patent it and then sell to a company in order to make money out of it, right? It's your time, your brain, so obviously you deserve the money that you earn. So in order to facilitate that, VLSI circuits have not only reduced the size of your electronic devices or electronic circuitry, but it has also given a facility to program it at the user's location. So the user can basically do the programming at their convenience. So it consists of millions of logic blocks, and it is surrounded by programmable input and output blocks that are connected together through programmable interconnections. So literally everything is programmable in an FPGA kit. So the performance of such devices is dependent upon the logic blocks and the efficiency of its programmed interconnections. So basically, how the device performance is totally at the hands of the user, because the user is programming it. A typical FPGA logic block would have lookup tables, multiplexers, gates, and flip-flops. The lookup table is a truth table, that is stored in the SRAM. Right? SRAM, we all know, is static random access memory. So by now, I'm assuming that all of you know about RAM and ROM and how the two are different and what exactly are these memories about. So to give you just a highlight of why we are using SRAM is because in SRAM you can actually write into the memory simultaneously. You can read from the memory and you can write into memory. So it provides a combinational circuit functions for the logic block. This is the lookup table. So the lookup table would actually decide the functions of the combinational circuit, and therefore decide exactly how your device is going to perform. The method of realizing the combinational function from the lookup table is similar to the method used for combinational circuit functions implemented using ROM. I'm sure you would have gone through this as well by now. So this section, along with numerous programmable multiplexers. So when I say this section, I mean the logic block. So this section, along with numerous programmable multiplexers, is used to configure the inputs of the flip-flops and the output of the logic block as a whole. Right? So your lookup table, or the SRAM, that is the lookup table stored in the SRAM, along with all the multiplexers and other, the flip-flops. So along with the multiplexers, sorry, I think I've gotten confused here. Hang on, let me just get this correct. So the truth table or the lookup table, along with the programmable multiplexers, is therefore used to configure the input of your flip-flops and the output of the logic block as a whole. So the RAM is used instead of ROM because, like I said, you can write into the memory if you're using RAM. However, the biggest disadvantage of using RAM is that the truth table has to be reloaded every time there's a disruption in the power. So if you're using a RAM, a static RAM to be precise, you have to make sure that you have uninterrupted power supply to your device, which is very, very hard to ensure. Even if it is a fraction of millisecond for which the power has been disrupted, the RAM goes clear. Right, so moving on. The program downloaded into the device can be done either through a host computer or through an onboard PROM. PROM is programmable read-only memory, right? So the program is erased. So if there is an already existing truth table or already existing program inside your device, then if you're rewriting another program, you can't just selectively rewrite it. The entire program is erased, and then your new set of coding is loaded into your device. Excuse me. So designing FPGA requires CAD tools, that is computer aided design tools, and this is used to facilitate the synthesis procedure. And everyone, if human being, if there are two human beings conversing, then both of them should be conversing in a language that the other understands. Similarly, if you are trying to converse with your computer, you have to have a certain language which the computer understands. So binary is the code that the computer understands. So you have certain interfacing languages such as C, C++, Java, .NET, and so on. You've got an ocean of languages with which you can program a computer, or you can write programs into a computer. So when you're dealing with FPGA, you have to have languages called the hardware description language. That is the only language your FPGA understands. So now the most popularly used one are Verilog, Able, and VHDL. So Xilinx is a company that actually is the sole reason for the progress of FPGA. Xilinx was the first company to commercialize FPGA, and the first commercially available was the vintage XC2000 device family series. Now this was followed by the XC3000 and XC4000 families as well. And finally, it set a path, or it set a stage for the development of the device systems such as the Spartan and the Vertex systems. So these are like the widely used FPGA systems on the modern day. The development and evolution of these devices has resulted in the density, improvement in the density, performance, power consumption, voltage levels, pin counts, and functionality. Miniature ICs have been available, which are very, very thin, which occupy very less space in the PCB. They are high performance. You can have very, very fast running ICs. Their power consumption is very, very less. As small as 3.3 millivolts is enough for an IC to function these days. Then you have the voltage levels and the number of pins that are available. Tiny IC with nearly 100 pins is also possible these days. And of course functionality. You can have an IC that is performing multiple tasks, which was not possible before FPGA or before VLSI development, to be very precise. Spartan and earlier device families consist of an array of configurable logic blocks, as also called as CBLs, the numerous global and local routing sources, I/O blocks, programmable I/O buffers, and an SRAM based memory. We shall discuss more on Xilinx FPGA Spartan system in our subsequent videos, because I think I have run out of time at the moment. I will see you again with another video soon. I hope you take care till then.